binary and denary, an introduction. Starting off, binary is either a 0 or a 1. So 0 and 1 are the only digits allowed in a binary system. However, in everyday life, we know we cannot get by just with that. We have to use our 10 base numbers, 0 to 9. 0 to 9 make up all the numbers we are used to. It is our denary or decimal number system. Going back to binary, one binary digit is a bit. 8 of these makes a byte, and a combination of bytes makes up words. And how many bytes make up a word really depends on the type of computer. For example, if you've got a 64-bit machine, it has a word size of 64 bits, which equals 8 bytes. Now let's look at the number system we are used to. Here's a number, 146. We must remind ourselves in the decimal system that the 1 is actually 100. So let's type 1 is 100. The 4 is actually our units of 10. And there's 4 of them. And the 6 is a singular unit. It's 1 unit of 6. So we've got 1 unit of 6, 4 of 10, and 100. And that is our typical denary system, working from right to left. As we go right, we multiply by tens. So 1, 10, 100. Now, we know that a computer can only store using binary, that's machine code, but we need to use denary. So there's got to be denary conversion. So you might be presented with the binary to find out what the denary is, or you might be presented with the denary and have to work out the binary. Let's look at this example here. We've been given the binary 1001010, and all we have to do to find out what our normal denary number equates to is to use these placeholder values. You will recognize these as our typical exponentials for bits and bytes. So 1s, 2s, 4s, 8s. What I mean by exponential is that this is 2 to the power of 1, this is 2 to the power of 2, this is 4 to the 2 to the power of 4, I beg your pardon, and 4 to the power of 2 to the power of 8. Oh, there it is written down there, look at that. So I won't forget. So exponentially, 2 to the power of 0, 1. 2 to the power of 1, 2. 2 to the power of 2, 4. So these are placeholder values to help us work out what did this binary number. And it's quite simple. We've got a 1 meaning on. So we can turn that yellow if you like. Select that as yellow. That means it's on. That's not been turned on. That's not been turned on, but that has been. And that has been. So what do we got? We got 128. And we can add that to the next binary that's been turned on, which is 16. And we can add that to the next one, which is a 2. These are our bit placeholders, if you like. 128 plus 16 plus 2, well, it equates to our original number, 146. So we'll just do a arrow 146, okay, or equals, if you like, 146. Right, well, let me give you the value of 1, denary 1. Well, it can only be the first one, the first placeholder. So what does this equate to? Very simply, 0, 128s, 64s, 32s, 16s, 8s, 4s, 2s, and 1, 1. So the binary for 1 is 00000001. Let's do another example. Right, let's work out 3. Let's go with the placeholders. It's going to be a 1, so we could bracket that and say 1 times 1, add it to our 2 times 1, which is 2, equals 3. So 1 times 1, 2 times 1, add them together, equals denary of 3. We'll go a little bit more complex now. Let's try the next one. Let's try denary of 6. The way I work it out is I try to sort everything out in my zeros and do the logical progression starting from right to left. We could try a 1 there, 1 times 1. So 1 times 1 equals 1. We'll add that to 2 times 1 equals 2, and we can add that to 4 times 1. So we'll get an answer of 4, 5, 6, 7. 7. So something's wrong. Most obvious thing to do is 0. So 1 times 0 is 0, add it to 2. Because 2 times 1 is 1. And how about having a 1 there? 4 times 1 is 4. 4 plus 2 is 6. There's our denary for 6. Let's go through that again. All I did was say, well, what happens if it was 1 times 1? That would be 1. What happens if it was 2 times 1? That would be 2, so that's 3. And add that to 4. 4 times 1, 4. That would be 7. So something's wrong. Let's take away that. Let's make it 0. So what's the answer for the binary? Well, the answer is 0, 0, 0, 0, 0, 1, 1, 0. And that is the number denary 6. I'm now going to pause to give you time to work out what 12 would be. If you want, you could try 1 times 1 equals 1. Add that to 2 times 1 equals 2. And we've got 7 over here. We know that from the previous example. If we had to have 4 times 1, which is 4. So that's 1 plus our 2, that's 3, plus our 4, which is 7. But we're barking up the wrong tree. Let's look higher up our placeholder values. We know that 8 plus 4 is 12. So if we just simply made that 1 and said 0, 0 plus 4 plus 8 will equal 12. So what's our binary? It's 0, 0. Whoops. What's our binary? Put a click in there. It's 0, 0, 0, 0, 1, 1. Oh, happened again. 0, 0, 0, 0, 1, 1, 0, 0. That's correct. That is our binary for 12. I'm now going to give you a larger number, a really large number, and let you work it out. Right, let's have 37. Well, one way to do it very quickly is to kick off with your highest placeholder. I've got a 32 there, so I'm just going to write that down in my mind, bracket it just to know that I'm thinking of 32. And 32 plus 4 will be 36, and plus 1 is 37. So let's try that. Let's try that as our binary. So we've got a 1 there. Let me just take that away. So I'm thinking of a 32. Yep, 1. I'm thinking of a 4. And I'm thinking of, yep, a 2. So that's 36. And a 1. So that's 37. Have you seen the mistake yet? Yep, we don't need that, do we? We've got the 4 and the 5 plus the 2 to be a 7, so 37. So what's our binary? It's 0, 0, 1, 0, 0, 1, 0, 1. And I think that's enough for now. Remember, if you have been told asked in the exam to work out or to convert denary to binary, you may use this placeholder, rough notes 1, 2, 4, 8, 16, 32, 64, and 128. What number does this take us to? What's the highest number? That's an interesting question, and that I'll leave to you. But it's in your textbook. Page, if I remember, can't remember right now. I think it's page 70 odd, probably around about 79. But you work out what's the highest number we can go to. There's a reason for that, and there's a reason why we then need to go into hexadecimal numbers, and so on and so forth. So that's for the next chapter.